Today I'll talk about thermal and bounded Unruh-DeWitt detectors in circular motion. First I'll talk about the context of this research, how it fits in to what we currently know. Then I'll talk about the detector schemes themselves and how we see what the detector sees. And then finally, I'll talk about the future trajectory of the work. So with respect to the context, first, we have to consider what the Unruh effect is to make sure everyone is on the same page. So the Unruh effect is that if we take a linearly accelerated observer, it will observe a thermal bath, whereas if you considered an inertial observer, it would see no temperature at all. So this phenomenon has an attributed temperature called the Unruh temperature, or sometimes the Davies Unruh temperature. And in natural units, this is just the proper acceleration divided by 2 pi. Now, in fact, this is exactly the same form as the Hawking temperature, but if you swap the proper acceleration for surface gravity, it's the same, which one could guess from the equivalence principle. So with the Unruh effect in mind, trying to measure this phenomenon, if we wanted to measure a temperature of 1 Kelvin, this would require an acceleration of the order 10 to the 20 meters per second squared, which is unfortunately rather unlikely to do, for example, in a lab. So to get around this, there have been experimental proposals, such as uniform circular motion in an analog system. Now, the analog systems will use a medium such as superfluid helium, Bose-Einstein condensates. Such experiments are being built, so superfluid helium at University of Nottingham and a BEC experiment at Technische Universität Wien are both being considered. And at the moment, in terms of uniform circular motion, the theory behind it, a good reference for the current understanding of this is in this paper by Biermann et al. So in order to detect something, we need to first consider a detector. This, in its most common state, prototypically is a 2-state detector, a ground and excited state in effectively 2+1 Minkowski space. The field that we probe with this detector is just some real massless scalar field, which we call phi. And then if we choose an appropriate interaction Hamiltonian, by this, I mean that whether we're considering a temperature or not determines which interaction Hamiltonian. This is because during the calculation, one finds the, one uses a Whiteman function, which in 2+1 dimensions, the thermal Whiteman function, if we used a coupling where we just take the field and multiply it by our detector monopole moment operator, which is representing our interaction. This is infrared divergent. So if we want a quantity that we can deal with, we instead use a derivative coupling to remove this divergence. So working to first order perturbation theory, we can calculate a transition probability, the probability that our detector will detect something, so go from its ground to its excited state. And by doing this calculation, one finds a constant prefactor, which has all the information regarding the detector, multiplying by this function f, which depends on E bar, which is our energy as measured from the lab. Now, this is what we call the response function, and if we want an explicit form, here it is. The chi represent switching of the interaction on and off, and for limitations, we consider infinite interaction time, so we can effectively ignore chi, take the interaction time to infinity, and divide out by the total interaction time. So then we can consider a detector rate. If we do this, and if we have a stationary trajectory, such as uniform circular motion, and measure with respect to a stationary state, then this expectation value we find in response function is actually also only a function of t minus t prime. So you can take this as a variable and easily divide out by the total interaction time. Now, if we take this entire scheme and apply it to the case of, for example, a bounded spacetime, this would be when we impose Dirichlet boundary conditions on our field phi, in particular on the field modes, to create an effective cavity at some radius that we will call r equals a. So here is our uniform circular motion. Capital omega is our circular velocity, angular velocity, and we want that omega times r, which is our velocity, is less than 1, i.e. less than the speed of light or the speed of sound in an analog system. If we do this, we get this double sum for our response function, and the function itself, we can well, it's just there. The points that are relevant are that our momenta and eigenfrequencies are actually discretized. And we can see that the delta function picks out each of the ticks of the detector. So we can explicitly see when the detector will see something. In contrasting this to if we just have a thermal background, we do not have such a delta function, and our frequencies are not discretized. So these are key differences. In fact, they depend smoothly on E bar, and our omega is m capital omega minus E bar. The n that we see is our thermal factor in this thermal response function, and the thermal part, i.e. the parts that are multiplied by our Bose factor, are even in E bar. And an interesting limit would be a Machian limit, i.e. tending towards the speed of sound in our medium. And if we do this, we find that the vacuum contribution, the first term in F, where our Bessel function J is multiplied by 1, not by the Bose factor, this is actually divergent, whereas the thermal part is convergent. This tells us that if we would consider a detector scheme near to the speed of sound in our analog system, it is the vacuum part that would be our leading contribution, and the thermal part would be negligible, depending how fast, how close to the speed of sound we're going. Now, if we would combine thermal and bounded regimes, it looks closer to our bounded system rather than our thermal system. This is because the boundary that we place affects our field modes at a base level, because we had to impose boundary conditions, as opposed to the thermal, which comes in later in the calculation. So this is why we have this discretization of eigenfrequencies still, as well as these delta peaks picking out each tick of the detector. We require both of these in order to model an experiment more effectively. So further from this, we can take analytic limits, such as the large boundary limit, and look at the leading and subleading orders. Currently, it looks like the leading order should be 1 over A. And similarly, in the thermal case, we can look at the large radius but constant speed limit. This is so we can approach inertial motion. And if we do this, the leading order contribution to this agrees with if we just took an inertial trajectory to start with, and didn't start with circular motion and then infinite radius. And then finally, a further limit would be looking at a modified dispersion relation. Since a superfluid helium and Bose-Einstein condensate, that they are the dispersion relations look different. We would have to modify omega to make this more accurate. And for BEC, this would be the Bogoliubov dispersion relation. And then we'd combine all three of these in order to model a experiment more accurately. So looking forward, this would be to numerically implement these response functions and see what a detector should see using the relevant experimental regimes. And finally, to add in finite interaction times, since most labs don't exist forever and can't do experiments forever. And that is it for time, and I have reached the end as well. Thank you.
Yep, thanks very much. Right now I don't see any audience questions. I have a quick one, which is, you mentioned early on the slightly tantalizing prospect that there are actually experiments or planned experiments for doing something similar to this. I mean,
yes.
What sort of timescale is that on?
So the superfluid helium ones are being built. I think they're hoping to be up and running. I don't know the exact time scale, but very soon, as far as I'm aware. And for BECs, I believe they're currently working, but I'm unsure with regards to this work, how close the experiments currently are to this. But
Sure.
Very close.
Okay, and one very hopefully quick question as well. Morgan Lynch says, nice talk. What Unruh temperature do you expect for rotational motion?
Oh, so I haven't actually calculated like the temperature. So finding the temperature uses what's called the detailed balance condition, and this is related to, if we take the response function f of e bar divided by f minus e bar and take its natural logarithm, then that's how we would calculate the temperature, but I haven't actually calculated that. The paper by Biemen et al. Doesn't look at bounded or thermal detectors, but does go in detail into the temperatures that you would expect for this uniform circular motion. So I'd recommend checking that out, because there's a lot of work on that on 3+1 and 2+1 dimensions. But I believe it depends on the energy scale you're looking at, from what I recall.
Great, thanks.